All right. So, hello everyone. Thank you very much for coming to this talk. Thank you very much for having us over. My name is Onur. I'm with LG Electronics. The title of my talk today is Spatial Sparsity Induced Prediction for Images and Video. And this is joint work with Ganghua. Gang is with TI now. And we actually did this work a while back when we were both, or at least started this work a while back when we were both with NTT Docomo. Docomo had a research lab in Palo Alto. And, well, I think they still do, but I think it's sort of mostly downsized now. All right, so here's an overview of the talk. So I'll describe a technique that generates some really interesting motion-compensated predictions for video. So, and the technique is useful in video compression, and the technique is also useful in whenever you want to predict one picture using another picture. And I'll show some other applications as well. So the types of things that it can deal with between the two pictures is focus changes. For example, you have one picture in focus and then the next picture is out of focus, let's say, or vice versa. Portions of the picture is in focus, out of focus, and that focus changes from one picture to the other picture. There could be brightness changes between the two pictures. There could be things like crossfades and blends and whatnot, and I'll show you examples of those. There can be noise, so one of the pictures can be corrupted with noise, and in fact can be corrupted with what I call clutter and interference, and I'll show examples of what those are. So in looking at this technique, this is not a new model for motion, so we're not going to be trying to propose new models for motion, sort of new ways of doing optical flow, etc. So the technique works with traditional motion compensation, block motion, affine motion, optical flow. And but what it can do is, because it forms better predictors than regular, let's say, simple predictors, it can help estimate better motion. And what I'll do throughout the talk is, initially I'll focus on two pictures that are aligned, but then we'll sort of take a look at results in video where there's motion, and also look at one application where we try to estimate better motion or better displacement between two frames. So in terms of basically things that I saw in Daala, Mozilla, some of you guys were over at our place and also at the Google VP Summit, and we got to learn a lot about Daala, and I think it's conceptually, this technique is conceptually related to some of the transform domain predictions done in Daala. I wouldn't say basically sort of very closely related, IP level related, etc., but basically conceptually, academically, let's say, I would say related to doing temporal and chroma predictions in Daala. So I'll then talk a little bit about how the technique does what it does. There are two viewpoints of that, and for that, and both are very useful. One viewpoint explains certain types of things that the technique can do, especially with the structured interference. And the other viewpoint establishes what type of linear distortions the technique can correct. And then basically at the end, I'll show you some results. So just to give you a background, so we started doing this work in 2006 or so, and that's basically the time when Docomo, I think, had the best phones in the market in Japan, and they had basically these nice phones, and a lot of the customers were looking at using their mobile phones to check out movie clips, etc. So the type of content that was delivered to the customer was things like this. For example, this is a commercial, I think, and commercial for Audi, some Audi TT-like automobile, but I think it's called Hurricane or so. It's going to come out at the end. So basically, so this is a commercial for an automobile, and the customer would be viewing this on their mobile phone in between, I don't know, viewing something else, I suppose. And this is a trailer for, I think, Sleepy Hollow. And so basically things like trailers and commercials, etc. And these things have a lot of scene changes. They have a lot of, let's say, blends, and there are a lot of sort of focus changes, brightness changes, etc., etc. And these were basically problem cases for the standard video codec at the time, so the AVC video codec, and we wanted to do something that handles basically built on AVC and made it better to handle these cases, let's say. So let me just sort of set the problem up in terms of what we want to do. So imagine, for example, on the left column there, I have X. X is what I called my anchor frame, and Y is the frame to be predicted. So basically, this column is my anchor frame, and the corresponding pictures on the right column are the frame to be predicted. The technique can be sort of straightforwardly extended to doing more than 2 frames, etc. You have a lot of frames in your frame buffer, so you want to deal with those cases, it can be done. So, but this is basically the fixed, simplest prediction setup that I think really shows the richness of the problem. So imagine, let's look at basically the first transition, the first temporal transition from X to Y. And here, there's some lightning, there's rain, there's clutter and noise, etc. Rain is different from this frame to the next. So on this frame, there's also rain, but it's different from the frame on the left side. And there's also this lightning depiction. So you try to basically compress Y using X with AVC at the time. AVC ends up encoding a lot of intro-macro blocks on Y, basically. And because it's not easy to predict Y using X. There's rain there, and there's that lightning depiction. Here's what is a crossfade transition from here to here. And notice, for example, here now we're changing from one scene to the next scene. We have I think the previous scene showing up with that big car on the left, and then on the next scene, the smaller version of the car starts showing. And this is basically a crossfade transition. You blend from one scene to the next scene. And the final one is this, where it says the hurricane. So, and there's that hurricane writing, and on the next frame, basically, there's that special effects transition. This clutter is there, and here it's not there. So how do I predict, in all these cases, how do I predict the right column from the corresponding picture on the left column? And that's basically what we want to do. And in doing so, we're going to be using causal prediction. So basically, there will be no magic of sending extra information. Oh, look, actually, there's a lightning there, please erase, etc. The algorithm that I'm going to present will magically figure out what is basically in frame X that is not needed in predicting frame Y. And it's going to do so causally. So everything can be done in a compression framework. So let me move Y to the right side and sort of show you what the predictions that this technique generates. So from X, it generates a prediction of Y. Notice here, for example, it figured out that this lightning depiction really needs to go. So basically, it figured out that needs to be erased. And in the crossfade, it sort of figured out, hey, this car is redundant. I'm going to get rid of that. And this car here, well, it needs to be brighter. So it figured that out. And again, this is a magical eraser technique. Here, it's looked at it and said, okay, basically this hurricane depiction, or basically that clutter there is redundant. We don't need that. And it figured out a better way to predict Y. So what the technique can be thought of as doing is it generates this in-between picture that is then passed on to regular motion compensation. So prior to running AVC, or prior to sort of inside the loop of AVC, prior to doing the prediction, you run this magical eraser and then do your regular prediction. And basically, that's the idea. The details of the technique, I think, is in an article that appeared in 2011 in Transactions on Image Processing. Okay, so let's look at basically the corruption model that we're targeting with this technique. And it's going to be a very simple technique, by the way. In fact, it's going to be something very related to what you guys are doing with doing transform domain prediction. And that thing would be like doing least squares. So basically doing very simple predictors. We just sort of do it in a different domain. So here's my anchor frame X, and X is actually the next frame plus noise. So this is basically a noise transition. From X to Y, you just have this noise transition. And this is the case, for example, when there's noise in the frames, when there's rain, etc., things like that. And this case alone is very easy, I think, is very well understood. I think it was very well understood 10 years ago. Effective denoising techniques have been in the literature, and some of the most effective techniques are, in fact, sort of doing these over-complete transforms, thresholding the coefficients, and inverse transforming, etc. And that's basically doing these translation invariant decompositions, but doing primarily thresholding. So here is, I think, the sort of the signature example of this technique. So here, in addition to this noise term, I have this what I call the structured interference. So I don't know if you can see it here. This is the image Peppers, and here we have Peppers plus Barbara. So the anchor frame has two images composited on top of one another. And here I'm showing color, but everything works grayscale as well. So we're not using color information. So how do I handle this case? Now noise is much more sophisticated. You cannot really, no longer you can do a transform, do thresholds, et cetera, to get rid of this, structured interference. You need to de-Barbara. So denoising is not sufficient. You need to figure out, hey, that Barbara is too much. You need to figure out a de-Barbering algorithm. And so this was basically, we wanted to handle this case. This was our signature example. We said, let's figure this one out. If we can do this, we can do all these other cases. That's how we felt. And I think we first we thought about optimizing the transform. So in denoising, you go to a transform domain and then do thresholding there. Well, maybe we can figure this transform out, and this new transform, we go to that transform domain and do thresholding. That didn't work out. We said rather than thresholding, maybe we can sort of zero out specific sets of coefficients, etc., try to figure that out. That didn't end up working. And what we wanted to do was everything we tried seemed to be working for isolated cases. And whereas we wanted something that worked all the time. And that's basically ended up being a lot easier than all the other techniques that we thought of at the time. So here is, okay, let me build on the corruption model a bit more. I also like the case where, okay, so there's a lighting transition. So L.y means I pixel-wise multiply y with a light map. And that's an amplitude modulation, and it makes the picture look like this. So now, at the top, my technique has to denoise. Over here, it needs to de-Barbara. Here, it needs to de-Barbara and then correct the light, correct the lighting change. Okay, so we also added this, basically, we will also be able to do this linear distortion in between, so such as a focus change. And in this case, what the technique needs to do is denoise, then de-Barbara, then do the lighting correction, and then do, for example, invert that filter S. Here, S is a filter. It can sort of signal a focus change or basically some other type of linear distortion, and it needs to figure out how to invert that as well. And the technique that I'm going to describe is going to be completely automated. It's completely blind. L, S, T, W statistics are not estimated nor known, basically, and it does basically the same thing all the time. I was reading the paper again, preparing for this presentation. I think I have a few good, we wrote a few good sentences. I don't know how many people read the paper, but we wrote a few good sentences. And I think one of them talks about this model robustness to modeling temporal evolutions and robustness to these temporal evolutions. Basically what it says is that the model robustness is so much so that the particular form of the temporal evolution, whether it's structured interference, noise, linear distortions, etc., does not even change the detail flow of the algorithm. So the technique is doing this very simple Humpty Dumpty type of processing, and it doesn't even know what it is correcting, so to speak. And it does the same processing regardless of the complicated overall temporal evolution. Okay, so let's talk about how the technique does what it does. And I think here we're going to use the first viewpoint. So the first viewpoint is in terms of doing these overcomplete decompositions. So overcomplete transforms, etc. And here I have, imagine I have this anchor frame. And here's my anchor frame. And it has Y, which is the frame to be predicted. It has that Barbara, annoying other picture in there, structured interference. And it has this noise term. So when you look at this picture, it's right here, and in every pixel there has contributions from Y, iota, and noise. And it's about, depending on the level of the noise, it has about equal contribution from Y and iota. So if you try to do things pixel-wise, you're not going to be very successful because half of the power you're getting is from Barbara, let's say, and half of the power you're getting is from your signal. So while in pixel domain, all pixels have equal contribution from both sources, Y and iota, in a sparsifying transform domain, if there is a sparsifying transform domain, we want it to be as depicted in this picture. So imagine I take a transform over the signal, this complicated linear transform, but it's basically a linear transform. And then it's basically, because it is linear, it can be written as so. So it's equivalent to taking a transform over y, and then a transform over iota, and a transform over noise. So sparsifying transforms are so that something like white noise typically generates insignificant coefficients, improbability. Most of the coefficients tend to be insignificant. And whereas structured signals, like my y and iota, they're going to have some significant coefficients. Now, the main assumption that we're making here is that there is such a transform where the significant coefficients of y and iota do not overlap, or do not overlap for the most part. And that's the primary assumption of this technique. And there will be cases where there will be overlaps, but I think we're betting that those overlaps are going to be few. And I think that's, in effect, the fundamental thing that allows this technique to be successful in doing these crossfades, et cetera, predicting over crossfades and whatnot. So this is the assumption. Now let's look at a real example, basically. And here I've taken the transform coefficients. I'm not telling you what the transform is yet, but basically these are the transform coefficients of pepper. And here I'm drawing the significant coefficients I've obtained over peppers. And dark blue means really significant coefficient, white means insignificant coefficients. And as you can, this is like an AC type of basis function that we're seeing here. And so as you can see, all the edges and sort of these high frequency detail, we can see clearly. Everything else is basically zero, very insignificant. And here I've done the same thing with Barbara, but I just color-coded it differently. So Barbara's significant coefficients, I decided to color-code them red. Okay, now over here, I have taken the transform of the composition. And what I've done is, for each significant coefficient I get, I try to decide, basically, this is just for drawing purposes, is most of that coefficient due to peppers or Barbara, just by doing magnitude comparisons. And if it is mostly peppers, then I colored it blue. If it is mostly Barbara, then I colored it red. If it's in between, a little bit of each, then I colored them magenta. I think you won't be able to see all the magenta detail very well, but the point is, you can see, in a picture like this, you can see the edges of Barbara and the edges of peppers very clearly. So a lot of the detail that makes that picture is still clearly visible in the blend. And I think this is basically a very important property of natural images. If you take, let's say, if you generate Gaussian processes with the signal covariance function, you generate one y, and then you generate one iota, you sum them up, and then suddenly basically it's another Gaussian process. You cannot tell that this is basically what you have now is a sum of two different things. I say pick two numbers, sum them up, and tell me what those numbers are. Okay, suppose you pick 2 and 3, and then you tell me it's 5. The sum is 5. I cannot tell that you picked 2 and 3. Maybe you picked 4.5 and 0.5, or basically, you know, all these sort of possible ways of getting to 5 are present. On natural images, that is not the case. On natural images, when you have a sum of two pictures, when you're looking at it, something like a blend, a crossfade, you can tell that there are two pictures there. And I think that's sort of the main idea here. So here is basically one schematic way of looking at natural images. Natural images live in non-convex sets. So non-convex means basically, I think, something like, we're calling them star-shaped sets. And so this is the set of natural, interesting images, whatever that means. So, here are, for example, things that are not in the natural images set. These are sort of, I don't know, noisy, very unnatural-looking things. And here we have Barbara, and here we have peppers, and in between is this image that we have. And this is, again, a schematic. I don't mean this diagram as a mathematical tool. But in between, we have this image. And it turns out that using this image, we can predict either this one or this one quite well. And that would be very difficult to do if, again, with a Gaussian process. Your SNR will be terrible. You'll be able to generate some prediction, but it's not going to be a good prediction. The main thing that allows it here is that images live in these non-convex sets. Okay, so How technical can I go in the description? Okay. Well. Okay. Okay. So far hasn't actually been important. All right. So this is basically where I want to discuss overcomplete transforms. Maybe again, lower percentage of individuals know what a DCT is and whatnot. Okay, all right. The discrete cosine transform. So it's basically like the way we generate these. Let me first describe it for the people who are knowledgeable, and then I'll try to back out of it a little bit. So imagine taking a discrete cosine transform basis function, a p by p basis function. You take the DC or the 0, 1 basis function, one of them, and then you run it through the entire image as a filter. And then that generates what we call basically a subband. And if you took the qt basis function, we're going to call that subband q. And that's going to, I think I have this, what is this Greek letter? I forgot Greek letters now. The zeta, is it? Anyway, there was a time when I knew about these things. So basically it generates this, let's call it zeta q. Amir, you would know these things? No? Okay. So imagine generating all of these subbands. So for a p by p DCT, there are p squared basis functions, and you'll be able to generate p squared subbands. And that ends up being a translation invariant discrete cosine transform. And once you have these subbands, what you can do is, I think one can easily show oneself that you can generate p square sets of discrete cosine transform coefficients for the image. So you, in effect, have generated p squared different transforms of the image, each one with a slightly shifted DCT. Point is basically, the way you have generated these things, there's a well-defined way of generating an inverse transform, even though it's an expansive transform, even though it's basically what's called an overcomplete transform. But I think for the signal processing knowledgeable individual, what we do is we have p squared filters, and we run, or basically it's like, you know, in audio, I suppose you have these filter banks, right? And then you separate lower frequency, intermediate frequency, higher frequency versions of the signal. And this is kind of like doing that. So basically you have p squared different channels, and you generate p squared different channels from the picture. And there's a well-defined way of generating those channels, and there's a well-defined way of coming back from the channels to reconstruct the picture. So similar to what is done here with the transform coefficient domain prediction, we generate the first subband, and then we generate the second subband, and all the way up to the p squared subbands. And we pretend that we generate some sort of an approximation to the picture that we're going to predict, and I'm going to show you how one can generate that. And then we generate subbands of that approximation as well. Based on those approximations, here's basically my detailed thing. Here is a subband of the anchor picture. Here's a subband of the approximation. We're looking at a particular coefficient. We establish neighborhoods around both of them. And in that neighborhood, we try to learn what is the best least squares fitting parameter that predicts this coefficient using this coefficient, let's say. And I think this is similar to the way, from what I understood, how things are done in chroma in Daala. So basically, it's sort of doing a least squares prediction in coefficient domain, except that we're doing it in basically the overcomplete DCT domain. So this is getting heavily technical, but let's try to sort of, again, let me quickly go through it. And the Daala team on IRC is very technical. So here is my anchor picture. My anchor picture is now simple. It has this sort of, I don't know, black and white picture and this other black and white picture summed together. It's averaged together, and it looks something like this. And my previously encoded, so this is my anchor picture, and the next picture is going to be, I think, this one, the first one. And here I'm a video coder now. And what I have done is I've encoded everything here, everything up to until this block. This red block, I have encoded everything. I'm pretending that I have done everything up to here, and I have received basically let's say, I've received Y until this point. So this is like a regular video coder. So I have done all the macro blocks until I come to this red macro block, or I've done all the blocks until I've come to this red block. So what I now do is I generate subbands from this picture. And I do not need to generate basically subbands over the entire picture, but I think let's pretend that I do. So here's the cute subband, what the cute subband looks like. It's sort of that, again, it shows significant coefficients because of this edge. And otherwise it's insignificant. And this red block, because of the way the filters are, ends up being a slightly larger block here. And my task is to figure out the subband coefficients of this block here. And the way I do that, so let's concentrate on this one coefficient here. I already have my previous frame, and in my previous frame, I've again done the subband decomposition, and it is color-coded. So from Y, I have this edge. From the iota, I have this other edge, and this pixel corresponds. This coefficient, I should say, corresponds to this coefficient, and these are the neighborhoods that I have that I'm going to do my least squares training in. So now over here, I do my least squares training. And what's going to happen if you look at these regions is it's going to say, okay, basically, whatever, the good least squares predictor is 1. So you can just copy stuff from the previous frame at this point. And then I move that by 1, and then repeat the same operation. Move that by 1, repeat the same operation, and sort of keep going about and predicting the stuff in the orange block. Once I have everything there, I'll be able to go back to pixel domain. And let me just skip how I go back to pixel domain. But in effect, what I want to do is fill all coefficients in the orange block and then invert. And I can do this in an encoder-decoder setting. Once I have the inverse, I have my prediction in pixel domain. I will subtract that prediction from the actual, and the encoder is going to send the prediction error, and the decoder is going to receive and put it together, etc. And then I have data for this block. Now that I have data for this block, I can move to the next block, etc., etc. But immediately, what you can see here is, for example, as this spot moves closer to this red, so suppose that X was exactly here. Now over here, there is no edge. So when that green neighborhood is here, it's going to be all zero, so to speak, in the predicted frame, in the approximation to the predicted frame. So the least squares is just going to say the best fit is just 0. And that's going to enable it to just kill this red edge, so to speak. Anyway, I think that's basically maybe too technical a discussion for this point. But in effect, the structured interference and all these sort of nasty edges that show up go away because of the property that we just discussed, because things separate in transform domain. And then it becomes just a matter of picking the right one, and the right one you learn from your causal neighborhood. Okay. Now, so I think there's another slide that will keep the Daala team very happy. So the way these channels are generated are through running filters. And one of the interesting questions that one can ask oneself, okay, so we can get rid of the structured interference, etc. But how about things like focus changes? How about linear distortions? Linear distortions end up being very important. And one can actually quantify, one can actually say that, well, this process with the least squares is in effect applying linear filters. So what it does is, it goes to the pass frame, it figures out a very small neighborhood, and in that neighborhood it trains a linear filter. And it trains, in fact, basically a particular class of Wiener filter, one can even say. It's just that it's not a fully parameterized Wiener filter. It's a rather simple or low parameter Wiener filter. And then in that neighborhood, it figures out that Wiener filter and then applies it and generates the prediction. So in effect, the entire operation is filtering of the anchor frame with particular filters. These filters change abruptly. These filters change spatially in a very, very adaptive way. But at each point, we're actually doing filtering. So then one can say that, well, if the anchor frame is, let's say, the predicted frame, the frame to be predicted with some filter applied on it, then can I invert that filter? So for example, if the anchor frame was a blurred version of my frame, then can I do deblurring, so to speak, with that process? Well, since I know the family of filters that I can realize with this, I can derive those, in fact, then I can say that if the inverse can be closely approximated by this filter set, by the type of filters that I can construct, then the answer is yes. I cannot construct all filters. My filters are going to have certain spatial support constraints, and they're going to have certain other constraints. For example, the filters with the DCT are going to be symmetric filters. If the filter is not symmetric, then I will have a symmetric approximation to it. But there's a certain class of filters derived in the paper, and if the linear distortion can be approximated by those filters, then I can invert it. Otherwise, it's going to be an approximation. So let's look at some examples that one can tackle with this technique. I now made all the examples grayscale because when you're showing color, there, for example, one picture is red, the other one is green, and then people say, yeah, of course you can separate it. Just keep the red and keep the green, etc. When it's grayscale, it's a lot tougher, so you cannot use any color information. And that's why we have basically everything in grayscale. So this is my anchor picture, and this is my target picture, and they're the same. They're both peppers, except that anchor has noise. And the PSNR of if one wanted to calculate PSNR, the PSNR of the anchor would be 34.16 dB because of the noise. And the prediction that we construct is at 36.47 dB. So we were able to come up with a predicted frame that is 2 dB better than the original anchor frame. So imagine, for example, the way we integrate this to AVC is normally AVC will predict this picture using this picture, and it will now have to encode the noise, so to speak. Whereas, because this minus this is going to be noise, and AVC will have to encode white noise, which then the decoder will have to subtract. So the decoder will have to get the white noise and subtract it from its anchor frame to generate a predicted frame, to generate the next frame, so to speak. Here what we're doing is, rather than letting AVC use this as the anchor, our implementation within AVC makes AVC use this anchor. That's, I think, the way to look at it. So here is a focus change. Okay, so noise anyone can handle, right? I could have denoised it, etc. Noise is easy. So here's a focus change. And in this case, I don't know if it's easy to see, maybe not. So it's actually, this is a blurred version of this picture. So here, the anchor is now a blurred version plus noise of this picture, and the anchor is now, it has dropped further down. It's at 30 dB or so, and now we're again at 32.22 dB. So we were able to again bump it up by 2.5 dB or so. And yeah, let me sort of move on. Generally, sort of doing these deblurring problems are more difficult than doing doing blurring problems. So let me show an example of this. So let's see if this is visible here. Well, if you look carefully, I'm not really sure you can see it or not, but there's sort of this ellipse around Barbara's head, and you can see it from here to here. Inside the ellipse, we have, this picture is sharp, and outside the ellipse, it's blurred. And the next frame is inside and outside is basically, it's at the same focus. So we're trying to simulate the case where something in the picture comes into focus, and because of that, something else goes out of focus. And the technique can now basically, the PSNR further drops. Now it's basically at, well, different picture. But so the PSNR is at 21.42 dB. If AVC had to do this, it will have to contend with this anchor. If you integrate our technique with an AVC, it goes up to 32.33. So immediately you start seeing huge gains now. And now we're talking like 10 plus dB gains, because we can figure out that it's a problem that we can easily correct. Here's one case where there's clutter. So we went basically, here my anchor frame is something I went and sort of took some graphics program and started drawing things on it. And this is basically sort of what we call clutter. And the next frame obviously doesn't have that clutter. If you have AVC now, it's going to intracode many things. Now, with our case, we can easily do the decluttering and generate something that is like, again, 10 dBs better predictor of the frame to be predicted. So let me go and do a fade example. Here is basically, we're doing this debarbarating now. And this is basically peppers plus Barbara over 2 plus some noise. And it's at 16.2 dB with respect to peppers. Obviously, terrible anchor. And with our technique, you can build that up to a 30 dB, around 30 dB anchor. So again, generating like 13 dB or so improvements. Here now, sort of, this is like now those infomercials, wait, there's more. So basically, I'm also throwing this other picture in it. So here I have peppers here, Barbara here, and both. I threw in both there as well. And then now the technique figures out, hey, basically we're predicting peppers here and generates a prediction of peppers. So it's like we were at 15 dB, and we are able to improve it by 12 dB or so. And okay, so wait, there's more. Here we have, so previously what we had was, we had the blend, right? And then the next picture was one of the blending things. Now we're making it more complicated if you think about it. This one is 0.3 peppers plus 0.7 Barbara. The next picture, it turns out, so we're going through a crossfade transition now. The next picture is now 0.7 peppers plus 0.3 Barbara. So you have these deblending techniques in the literature. You applied them. It's not going to work because they try to isolate individual things from a blended picture. We're not. We're trying to predict a different blend from one blend. And the anchor picture is at 18 dB now, and our prediction goes up to 31 dB, again, something like 13 dBs. Again, sort of look at the magical aspect of it. So using those causal windows, the way these things work is that we first transmit this little 4x4 block, and then use everything bootstrapping from that. Sort of predict the next, predict the next, predict the next, based on learning from the causal neighborhood. And there are certain problems with causal learning. I'm sure you guys are also sort of aware of that. But I think overall it ends up working quite well. But it basically generates these magical results. The technique figures out what portion that the new thing is supposed to be blended. So it figures out peppers, it figures out Barbara, and amplifies one, reduces the other. So if you look at it from this macro peppers versus Barbara thing, it sounds really magical. But it's actually a very sort of low-down, very simple technique. So wait, there's more. Billy Mays passed away, but I've learned. They had this show on Discovery, I think, the Pitchman. Sort of, they tell you how to sort of pitch the product and whatnot. So I've learned a few skills. So one of them is wait, there's more business. So here we have a blend, and on top of that blend, we have this lighting change applied. So the technique now has to denoise, debarbara, and undo the lighting change. And so the original anchor is at 10 dB. Now we're basically, the anchor we provide is going to be around 27 dB. So that's like a 17 dB improvement. Okay, so those are basically a bunch of pictures, and we wanted to run this on video, so we actually did a full integration with an AVC. Everything works out fine, encoder, decoder, so on and so forth. And this is, again, work we've done around 2006, 2007-ish or so. And at the time, the best video codec is AVC, so we were sort of trying to beat up on AVC, especially on these types of video that we identified as our targets. So here's basically this crossfade transition. And I think we encoded these 5 frames. First frame is encoded intra, and then everything is encoded PP. And we're just looking at the performance over P's in a very healthy way. We know how to do these things. So here, for example, it's possible to get something like 25% gains in rate in encoding this type of sequence. So we're first looking at individual problem elements and how much gain we get in these individual problem elements. So it's not to say that all video sequences, it only works on these video sequences, etc. It's just a sort of what happens. Okay, we're doing better prediction. So I think that's an important point. So let me state that. So in modern video coders, there are many sort of different prediction paths. And you can generate really good predictions, but at the encoding rate distortion optimization loop, you will get thrown out because something else ends up working a little bit better, so on and so forth. You're not particularly friendly to the coding syntax, your predictions, so you're going to get thrown out by the encoder. So we wanted to sort of put it in and see that it works in an RD framework. And the initial things we tried were basically these problem cases, because we thought that, okay, we're generating 10 dB better anchor frame, so that has to count for something. Does it or does it not? Let's figure it out. So here again, basically, this is that sort of this lightning transition. There's this lightning going on and rain and etc. And we're able to generate like 7% gains in rate for this particular transition. And this is the special effects transition, and we're again able to generate like 10% gains in rate. On that movie trailer I showed you, I think the Sleepy Hollow trailer, and because the trailer itself contains a lot of these sort of problem cases that we really like, we're able to generate like 20% improvements over the entire trailer. So now we're talking something like 450 frames of video, and it has a lot of motion, etc., and all these different types of changes. We looked at, I think, simple cases like Foreman, or basically Container, all these sort of interesting video sequences. These are very boring stuff. So on the boring stuff, we got like 2 to 5% improvements depending on the video. But I think, so my team at the time was doing the Docomo's entry into the HEVC competition. And it turned out that, for example, at the time, you start with let's say, a baseline codec, let's say AVC, and then you add more tools to it. And then you generate the new codec, so to speak. And it turned out, I think, on the average, each tool got like 2% improvements, so 2-3% improvements. So I think this tool was, again, sort of, even on the boring sequences, it was a worthy addition to build a new codec. So what other things, basically, what other applications of this type of technology is there? So for example, let's look at this case. This is, again, sort of from the video I showed you. So there's this lightning, etc. stuff here. In anchor frame, you have this lightning, you have this rain, and then in the other frame, you don't have any of that. You basically just have rain, I suppose. So if you ask the question, does anchor frame A or does frame A match frame B? A human being looks at it, of course, yes, they match. Basically, I see the same scene behind the lightning. But if you try to do it with a computer, if you try to do the comparison with a computer, then the answer is basically no. You have to go to the sophisticated feature-based things, etc., etc. But then it's a matter of which features you use. Okay, SIFT runs okay here, but fails on things that have a lot of corners and whatnot. And so for this technique, it's basically very easy. It does this. It uses some causal information from here, and then it removes that lightning. And now you can do the straightforward comparison again. You can again use the old not so bright computer. Okay, you convert the question, does A match to B, to does A prime match B? And in this case, the computer is going to say, yes, they match. So that's basically useful in doing things like multimodal imaging, for example. You take some hyperspectral picture, some things are there, some things are missing. You still want to be able to say, okay, these are similar pictures and whatnot. We did one example with the medical images. So here's basically some, this is my anchor column, and this is my target column. And what we're trying to do here is we're trying to align these two images. And in medical space, people try to do those things. And it can be, for example, that this is X-ray and this is MRI, for example. Here we have this case of clean images. This image is in effect here, this one rotated to the right a little bit. And this is the ground truth warp. So if you know the actual ground truth warp, you say that, okay, I took this and then rotated a little bit to the right, and this is what I got. And we took somebody's technique. It's one of the sort of the better techniques in this space. They calculate these affine warps between images, and they're noise robust, and it's a very good technique. So we took their technique, and I think on this column we're running that technique. Right, and we call that technique the baseline method. But basically, on this column we're running that technique, and on this column we're running that technique again, but we worked in our prediction. So in each and every time, it has this sort of warp search thingy, and inside that warp search loop, we put our predictions in there so that we always give it a better anchor. Okay, so this is basically everybody's got the correct warp. Okay, so the difference between the calculated warp and the calculated warp and the ground truth is like 0.08 or something, And with our additions, it became, well, again, something small. Now here we started adding noise. We added a lot of noise, and then, okay, so let's calculate the warp now. And this is the ground truth one. This is how it should look. This is what the really good technique did. So basically it screwed up. It calculated the wrong warp. It misaligned the two pictures. With our case, it was able to do it again correctly. Here we basically added, I think, some sine wave or something, and again, a lot of distortion added, obviously. And the baseline technique did not figure it out correctly, whereas basically the baseline with our additions was able to do it correctly. So this is basically a way where you take this fixed affine warp package, the package that figures out affine distortions, you add our technique to it, and it's able to calculate sort of better estimates of what it does. Here, basically, two images fused together, and again, this is what the ground truth, this is how the rotated thing should look like, and this is what the baseline technique calculated, and this is how the baseline fared after we integrated SIP into it. Okay. So I have some basically complexity numbers here, but the actual implementation that we did ended up being a lot less complex because we figured out all these sort of really shortcuts. So you don't have to do all of the overcomplete transforms. You basically don't have to do the least squares training all the time, etc. And basically you try to lower your complexity as much as possible. And I think we did a good job. So I think it was not as bad as what is depicted here. And even this one is manageable, I think. I don't really remember exact numbers of how much more we made the AVC decoder more complex. Because this is the version of the technology that learns things in a causal window. The decoder has to replicate some of the computations that the encoder does. But there's a way of, and that's what we were doing at some point, not do it on a causal window, but actually send parameters forward as overhead. And that's, I think, lowers decoder complexity substantially more. So I think I want to say a few things with respect to other work. There, for example, a lot of these techniques on video, people have applied, okay, brightness, there are brightness changes. Let's figure out a technique that takes care of brightness changes. And I think there's a paper by these Japanese authors that was done maybe late 90s or early 2000. They have basically brightness changes, but it only does brightness changes, of course, nothing else. There are Wiener filter-based subpixel interpolation. I think these got called in HEVC development adaptive interpolation filters and whatnot. They're not really interpolation. They're basically, it's like a filter dictionary. And the thing is, and I think this is discussed in the paper, these filters are formulated in pixel domain, and they're sort of big filters. So to learn big filters, you have to learn them over large neighborhoods. When you learn things over large neighborhoods, this low-pass thingies end up creeping in because a lot of the temporal evolution is characterized by these low-pass filters. So they really do not have the capacity to adapt quickly. And they also need many filters in the dictionary. And I think with respect to AIF and brightness compensation techniques, in our internal tests, we always fared better. Things got basically more convoluted when you combined, for example, these interpolation techniques and brightness compensation techniques, and compared to basically doing our way, then they ended up being more competitive with us. Then things basically started getting sort of, okay, we're maybe 1% better than the combination or something, over boring sequences. Over interesting sequences, we're again, 5%, 10% better. So there's a tool in video compression. It's called weighted prediction. And that's like, so suppose you have this, let's say, a crossfade going from scene A to scene B. So here is like 100% scene A. Here is 100% scene B. In between is like A, B, A, B, A, B, A, B. So it's basically going from one to the other. And weighted prediction says, okay, so when you're encoding something like this, why don't you basically encode A, and then you encode B, and in between you can sort of do the blending and sort of come up with a compression tool like that. Okay, that's interesting. So one can sort of do this delayed type of encoding with weighted prediction. But in cases, for example, of low delay, In cases where the two frames are not in the clear, then you cannot do it. And those are, I think, the bulk of the cases. And basically, I think what our technique does is in things like crossfades and blends, it allows you to do accurate prediction with no frame delay. So you don't have to go forward and figure out this clean frame and go backward, figure out another clean frame and sort of try to blend them and come up with a better anchor for yourself. So this is my last slide. So there are basically two ways of looking at this work. One is through these overcomplete transforms, and that allows us to see how the work will get rid of things like Barbara, so how it's going to get rid of things like the structured interference. And the other way is basically sort of looking at it through these really localized filters, linear filters, so adaptive filters that get applied spatially and that very quickly adapt spatially. The paper identifies these trade-offs. If you want to adapt quickly, you need to learn quickly. If you want to learn quickly, you cannot have that many parameters. So if you try to learn general filters, then you're going to screw up. So what this work does, in effect, is it restricts the class of filters to a manageable reduced parameter family that can be learned rapidly and that can be learned effectively inside small neighborhoods. So I think that's basically the macro or high-level viewpoint to this technique. So again, many types of temporal evolutions this technique handles. It can be does denoising, remove lightning, handle complicated fades, focus changes, etc. And the algorithm is not at all impacted by having one transition versus another. It's basically, again, this low-level, simple algorithm that does these least squares computations in coefficient transform domain. So it targets modern video, movie clips, special effects, sports, etc., and these boring sequences, I suppose. It also targets them with reduced gains. And I think it basically a power of the sparsity compositions and the non-convexity of images and video, because otherwise, as I said, somebody tells you, okay, I summed up two numbers and the result is 5, there's no way of guessing, basically. If the two numbers are in some sort of convex domain, then there are many answers that give you 5. But images are not like that. Okay, so I think that's basically my last slide. And if you have any questions, I'll be happy to answer them. Thanks for listening.
Thanks. So I have a few. Can you talk a little bit more about how you actually do the least squares fit? Like, are you trying to predict one coefficient in one subband from other coefficients in the same subband, or are you looking at other subbands?
So basically, this is strictly interpicture. So predict the coefficient in this picture's subband Q using this same coefficient in the previous picture subband Q. You can make it more complicated. You can say, okay, I'm going to predict subband Q coefficient using all the subband coefficients at the same location. You can make it more complicated, but we did not do so.
Oh, and sorry, you don't have a microphone. The people who are remote asked if you could repeat the questions.
Okay, so, can you?
Right. So I was asking if you're predicting one coefficient in one subband from other coefficients in other subbands, or just other coefficients in the same subband.
Okay, so the question is about how the each coefficient is predicted, whether a coefficient in a subband is predicted using, let's say, the same coefficient in the previous frame, same subband, or other subbands are involved, or basically, are there other coefficients from the current frame involved? No. So prediction of the current frame's particular subband coefficient is done with the same coefficient in the previous frame, so to speak. Does that make sense?
I think so, yeah.
The other coefficients within the same subband from this frame and the previous frame are used to train the least squares. And you don't even have all of the coefficients, so you have, in this frame, you have approximate versions of those coefficients. So you still try to fit this least squares to some noisy data, let's say.
So Jean-Marc asks, what exactly is overcomplete helping buying you over greatly sampled?
I think critically sampled is going to be very blocked and very.
Repeat the question. Sorry.
What does overcomplete buy you, or an overcomplete decomposition buy you over a critically sampled decomposition? And so if we repeated the same thing with the critically sampled, it's going to first of all look very blocky. And the second thing it's going to look is it's going to reduce the impact of the prediction. So let me just sort of go to this picture here. So the thing that overcomplete decompositions buy you is that you're never doing all that well when you're on top of an edge, let's say. But around the edges, you're sort of really doing well. So when there are no sort of clutter, etc. around, you're really doing so. With the overcomplete decomposition, you generate a lot of these accurate zero predictions. Okay, this thing should be zero, this thing should be zero. Whereas for the larger coefficients, you're sort of generating okay. But the way the overcomplete is inverted, those good zero predictions allow you to sort of generate better predictions for the other stuff as well. I don't know if that makes sense. So I think there's that basically that the way the overcomplete is inverted, I think, gives better insight into that. But it gives better prediction, and it also sort of gets rid of things like blocking and whatnot.
Right. And so Jean-Marc also asked if the overcomplete decomposition is used just for the least squares parameter estimation, or also used to predict less than one block at a time.
Okay, so the question is the overcomplete decomposition used to just to train the least squares, or is it also used in prediction? It's used in least squares and in prediction as well. So we predict the entire overcomplete subband. So we take the previous frame's overcomplete subband and we use that to predict this frame's overcomplete subband. So we always generate p squared. So the number of predictions that we generate is p squared more than p squared times a critically decimated prediction would be.
Do you recall if the divisions in your algorithm are by constants, or are they variable?
So the question is, are the divisions constants or are they variable? So I think there are several things. First of all, there's a lot of magic involved in sort of calculating the least squares fit. You can do the sort of actually calculate the least squares. You can do some lookup tables there, etc., and there may be divisions there, but I'm not really sure if you need, maybe you need some divisions there. But let me sort of separate that from the overcomplete decomposition. In the overcomplete decomposition, again, when you're doing inverses, etc., you do need some divisions, but those can be thrown into lookup tables. Basically, you can sort of do these multiply by the inverse. So they're with respect to constant numbers, I should say. So you can just multiply with the inverse of it. But the least squares is up to you, I think. Least squares, you can do simple things, computationally simple things, or computationally more complex things.
So in your integration with ABC, were you putting your technique inside the motion vector search as well, or just using that?
So we ended up doing that. So I think, and we generated some. I'm sorry.
Repeat the question.
Oh, sorry. So in ABC integration, did we put the technique in the encoder side? Did we put the technique in the motion search, or did we sort of first calculate motion and then apply the technique, so to speak? We did both cases. We were not satisfied with the gains with basically the motion just calculated in advance. On the run-of-the-mill videos or the boring stuff, it probably doesn't make that much of a difference. But on things like these blends or on sort of more sophisticated things, if you don't put it there, put it inside the motion search, then the motion search thinks those things are horrible predictors. So it's not going to go there even.
One thing that's interesting for the room is that you actually have code for example implementation that's online.
Yes, we do.
Yeah. I played with it a while back, and I tried it without motion search, and on blended images, it didn't work very well. I wondered how you made it work with the motion. Now I can see it put it in the limit.
So the AVC integration, I think, is we did a lot of work there, and in fact, with the AVC, I don't know if HEVC is also like that. I think sort of within a macro block, the way it sort of goes about those little 4x4 blocks is not straightforward. It sort of does this, and it does these weird scans in there. And all of those scans are problematic. So you have to write separate code for each and every one of them. And it got a little hectic because of that. But that's just the AVC's fault, so to speak.
Yeah, HEVC is worse.
HEVC is worse is the comment from the floor.
Did you try anything other than the least square?
Did we try anything other than least squares? Yes, we tried basic.
P square in the over complete.
What do you mean by that?
Like do every other pixel.
Yes.
Oh yes. So the question is, did you try anything other than being fully over complete? So rather than being p squared over complete, did you try other things? Yes, we have, and basically, sort of some of the things that work well are sort of that lower complexity are those things. So you skip every other, and I think these are probably all in the patents by now, but so obvious things, for example, like you do this, on this row you skip, let's say, the odd ones, on the next row you skip the even ones, and basically things like that. All these sort of diabolical extensions are possible, and they end up working. They end up working reasonably well. And I think for least squares, let me answer a question that has not been asked. On least squares, we actually tried several things because, in video, it really gets quite hectic. And you look at the least squares predictions that you're doing, you have very little data, and you're trying to learn something. So we wanted to go heavy on the least squares. Can we make it more robust? So we did these robust fitting sort of things, etc. And none of them ended up working to a level of satisfaction, basically, that gave really huge gains. And just doing the simplest least squares ended up working as well as the more sophisticated techniques.
Yeah, well, I mean, you only have a small amount of data to train on, right?
That's right.
There's people who say, like, when you only have, like, very little amount of stuff to train on, like, sometimes just taking some average is the best thing you can do.
Exactly, exactly. So I think the question is when you don't have that much data, I think the things that you can do, basically the simple things end up working better than more sophisticated things. And I think this technique is primarily based on what is the best that I can do with very little data. Because if you look at the predictions that the technique generates, on this location, it sort of does this low-pass filtering type of thing. And in a very close location, it starts doing this high-pass filtering type of thing. So you drastically change your filters from one location to the next. And to do that, you really need to simplify the problem because you cannot learn otherwise.
So Jean-Marc wants to know how well it works on blocks that have significant coefficients from multiple images, like edges from Pepper and Barber that cross.
So the question is, how well does it work when edges overlap? I think when edges overlap, it starts to work not that well. And it turns out basically, so we were very concerned about this. Basically, we said, we're always trying to improve performance. We're never satisfied with performance, so we always try to improve things. And one of the things we tried was, okay, so if edge is also spatially continuous, let's say, then maybe I can predict those locations and start doing more sophisticated things. We never ended up getting huge gains from those. But that's probably because maybe we didn't expend enough energy on it. The thing is, these overlap locations end up being not that many, so to speak. And any time, I think, when there's significant overlap, you end up sending an intro block, let's say. So it ends up sort of compensating itself that way. But no, so it doesn't work that well when there are overlaps.
Is it better or worse than just doing straight copying the previous frame?
So the question is, in overlaps, is it better or worse than doing straight copying? I think in overlaps, what ends up happening is it either does a semi-decent job, or it doesn't do a good enough job, and then the RD optimization at the encoder throws it out and sends basically an intra-macro block or something. But at some point, we looked at the number of intra-macro blocks we were encoding with our extended AVC, and it was, I think, substantially below. On the problem cases, it was substantially below the what regular AVC did, percentage-wise.
Do you have a ballpark for what substantially?
It's been a long time. I think I don't have any good guesses on that.
Yeah, Jean-Marc also wanted to know if it's mostly a blockwise switch where you predict like Pepper or like Barbara. Are you?
So the question is there sort of switch that tells basically whether you're predicting like Pepper or like Barbara? Is it block level? So it is not block level. It's in effect sort of, it gets constantly learned. So I think when you're, let's say, suppose when the two edges are crossing one another, as you're getting away from the edge, it becomes easy to learn, okay, this is peppers, 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 peppers. And you learn it per coefficient because you're always doing these least squares, solving these least squares problems. And as you get close to that overlap now, basically it now becomes, it's peppers, no, it's Barbara, it's peppers, no, it's Barbara, and then sort of whatever happens, you either encode it as intra, the prediction is not good enough, or basically, or it's a reasonably good enough prediction, and then you still end up using the technique. But I think it's a continuum, so to speak. So it's not this, inside this block, it's guaranteed to be peppers, inside this block. So this basically, it just generates pixel domain predictions, and it does it in a very simple loop, and it's in a continuum, so to speak. But I think so. For example, just sort of talking about when you're doing this chroma prediction in transform domain, I think if you generated, let's say, if you allowed yourself to go 4 times expansive, if you generated these in between, let's say, coefficients, and also predicted those using your chroma scheme, for example, and then did the inverse transform and blah, blah, blah. You guys don't inverse transform, but if you did, I think you will end up generating better predictions for your chroma. So basically, by getting expansive, you will be able to generate better chroma predictions as well. But I know your entire pipeline is in coefficient domain, but...
That seems to be the end of the questions. So, everybody give one round of applause again.
Thank you very much.
Certainly a very interesting technique.
Thank you all very much for coming again.